Bob Manning is a systems engineer for British Rail.
Signalling systems are broken down broadly into two parts: the safety side of systems and the indication and control. On the safety side, most people are familiar with the mechanical type of lever frame with the interlocking that was provided there. From there we move forward to relay-based interlockings and now into the modern computer-based solid-state interlocking. On the indication and control side of things, the original mechanical box had a simple mimic display. This was superseded by a panel with push-button controls, and in recent years by a VDU display system for the signalman.
The separation of safety interlocking from the other parts of the signalling system is vital to a railway which carries millions of people every day. Later in the programme, we'll look at the way computers are being introduced into the safety systems. But first, we'll see how they can help the signalman carry out his day-to-day duties. The display system in the signal box here at Leicester is run by computer. On the wall, there's a diagram of the track layout for the area covered by the signal box. Around 60 miles of main line between Bedford and Loughborough. There are lamps on the display to represent signals. Each signal has a number for identification, and the numbers are shown on the signals themselves. This signal, number 416, is at the end of platform 3. Back on the display, the track itself can be illuminated to show if a route has been set. For the signalman, a route is just a section of track from one signal to the next. Setting a route involves checking that the track between the two signals is clear. If it is, then the signal at the entrance to the route can be changed, so that a train can move forward. If the track plan on the display shows red, that means there's an obstruction on the track. Possibly a train is present. That information comes from an electrical monitoring system called a track circuit. This can detect whenever a metal object touches both rails of the track. Trains have metal wheels and axles, so if even a single coach is on the track, the circuit is completed and an indication sent to the signal box. To operate the signalling system, the signalman has another copy of the track layout on his desk, with a push button for each signal. Setting a route involves pressing buttons for successive signals down the line. The system then changes the points and signals appropriately. To see the system in action, we'll go down to the station, where the 1525 to London is waiting at platform 4, ready to depart. In the signal box, this train is known by a train code. It's the 1C65. Class 1 trains are mainline passenger trains. The signal at the end of the platform is number 418. So that's the button the signalman will have to press. The next signal is number 404. Pressing these two buttons sets the route between the two signals. Signal 418 turns green, and the route to signal 404 lights up. And by pressing a sequence of buttons, a succession of routes can be set up. Meanwhile, down on the platform, the train gets ready to depart. As the track circuit detects the train's new position, it's shown in red on the display. And of course the signal changes from green to red as the train goes past. Now, to provide these displays for the signalman and to process the information from the push buttons, the computer system needs to contain a representation of the track layout being controlled. Although the track layout may be quite complicated, the data structure used here is fairly simple. It just has to list the allowable routes. The first part of the data structure is like a sequence of records. It's a list of all the different signals which can be used for the entry to a route. The record for each entry signal refers to another sequence, showing the possible exit signals and the corresponding route number. We can see how this works by looking at what happens when a route is selected. Suppose the signalman presses button 409 for a train coming into the station. There are 4 platforms in the station, together with a siding. So there are 5 possible exits for the route. If the signalman presses button 419, the computer will search the list of allowable exits until it finds number 419. That will give the route number. If a train comes on the other track, the entry signal will be 407. This time, there are only 2 possible exits. It isn't possible to get to platform 3 or 4 from here. So if button 419 is pressed by mistake, it won't be found in the exit list. If this happens, the system just ignores the route. The signalman will have to enter it again. But checking for a valid route is only part of the problem. Let's go a little further out from the station, to signal 397. This is the first signal on the station approach, which is seen by the northbound trains from London. After passing it, through trains would go straight on. But this terminating train crosses over to the right-hand track. That's the track normally used by southbound trains. The reason is that this terminating train is due at platform 4. And that's on the right-hand side of the station. So, while this manoeuvre is taking place, the southbound line is blocked. And it remains blocked until the terminating train is safely in its platform and the points can be changed back. So a vital task for the signalling system is to handle conflicting routes. If one route is set, the system mustn't permit another route which interferes with it. Bob Manning.
The safety side of a signalling system is basically termed the interlocking. This is because it interlocks the points and signals to prevent any incorrect movements taking place. On the early type of mechanical interlocking, this was achieved by mechanical mechanisms within the lever frame itself, later supplemented by electrical controls to control the overall system. As we've moved to the relay-based type interlockings, the physical interlocking is achieved totally by electrical circuitry. We're now moving towards the solid-state interlocking, which we're now installing. This achieves the interlocking function by means of safety-critical software within a safety-critically designed system.
In the signal box at Leicester, electromechanical relays are used for the interlocking. There's a large room at the bottom of the signal box containing thousands of these relays, one for each component of a signal or a set of points. You could think of them as forming a kind of computer. The technology is slightly old-fashioned, but that means it's been tried and tested, vital where safety is concerned. Whenever a signalman selects a route, the corresponding relays click into action. They're wired up so that they can only set the route and turn the signal to green if it's safe to do so, if no conflicting routes have been set up. For instance, take the southern approach to Leicester Station. The northbound route to platform 4 is this one, 397 409 419. The southbound route from platform 3 is this one, 416 404. Each of these is a valid route, but they interfere with each other. So if one of these routes has been set up, the interlocking must make sure that the other one isn't allowed. Although much of the interlocking on British Rail is based on electromechanical systems, computer-based interlocking